Hello everyone, this is exercise class 2 and I will go through the solution of the question step by step. For question 1, you are given a vector field and you are asked to chart the Stokes theorems around a circular path of radius r centered at the origins in the xy plane. So the Stokes theorem states that when you do the integrals of the curls of a vector field over an area, and that integral is exactly equals to the path integral that you perform the vector field along the boundary of the area. So in the question, you are asked to do the integration over a circular path, and which means when you do the curls of the vector field over the circular area here, and the integral in the left-hand side will be exactly equals to the path integrals of the vector field along the circular path. So to determine the directions of the path integrals, you can make use of the right-hand rule. So first you point your right thumb to the directions of the normal vector of the area. So here we have chosen the normal vector to be pointing to the z-axis. So now you point your right thumb to the z-axis, and then the directions of your other fingers that curls will be the direction of the integration of this path integral, so which is anticlockwise. So first we compute the curls of these vector fields. So first you write down the matrix, and then you compute the determinant by following the rules. So here the x component will give you rho y 0 minus rho z bx, which is 0. And then the y component is rho z ay minus rho x 0, which is also 0. And then for the z component, it is rho x bx minus rho y by, which is b minus 2. So the curl is just b minus a z hat. And then the dA here is simply dA z hat. We have chosen the both vector to be pointing to the z directions. Then we put the two components together, and then we do the dot product. So the integral is simply b minus a dA. And because the integrand is b minus a, which is a constant, so here is simply b minus a multiplied by the area of the region here enclosed by the circular path, so which is pi r squared. So we have pi r squared b minus a. And then we evaluate the path integrals along the circular path. So because we are integrating along the circular path, so it will be more convenient to parameterize the path by the polar angle phi. So the R here is the position vectors of the point along the path here. So it is R cosine phi x hat plus R sine phi y hat. And then the dr will be simply taking the differential of the vector here. So here is minus R sine phi d phi x hat plus R cosine phi d phi y hat. And then for the vector field, we replace the y with R sine phi and x with R cosine phi. Then we put the two components into the integrals, and then we do the dot product. Then we have these expressions. So here we just need to do the integral of the sine square phi and the whole size we find from 0 to 2 pi. Because we are doing the integral of a closed loop, so the phi will go from 0 to 2 pi. And the integral of the sine square phi and the cosine square phi are both pi. So when we combine them together, we will have pi r squared times b minus a, which is exactly equal to the area integrals in the left-hand side of the Stokes theorem. So now we have tried that the Stokes theorem is correct in the example. So in question 2, you're asked to check the divergence theorem for the functions V here and use the volumes of an octant of the sphere of radius r. The divergence theorem states that the integrals of the divergence of a vector field V over a volume is exactly equal to the surface integrals of the vector field V over the boundary of that volume. So in the questions, we're considering an octant of a sphere. So the volume here will be correspond to the volume of this octant, and the surface integrals here will involve the 4 surfaces over this octant. One is the curved surface, and the other 3 are the quarter circles in the xy, yz, and xz planes. So first we try to evaluate the left-hand side of the theorems. Then because the vector field is different in the spectral coordinates, so you have to use the divergence in the spectral coordinates to compute it. And I have given you the formula in the question, so there shouldn't be any problem. You just plug in the vector field V into that expression, and then you should be able to get the divergence of that vector field to be 4r cosine theta. Then we put the divergence of the vector field into the integrals and integrate over the octant. The dv here is r squared sine theta dr d theta d phi. And the domain of integration would be integrating r from 0 to capital R and theta from 0 to pi over 2 and phi from 0 to pi over 2. Then we can do the integration separately. Then for the phi part here, it will give you pi over 2, and the r part here, it will give you r to the power 4 over 4, and the theta part here, it will give you 1 over 2. Then when combining them together, you will get pi r to the power 4 over 4. Then we try to evaluate the right-hand side, which is the surface integrals of the divergence theorem, and there are 4 surfaces to integrate, which is the curved surface and the other 3 quarter circles. So we can decompose the surface integrals into 4 different integrals. Then we first consider the integrals over the curved surface. So over this curved surface, the R is fixed to be the capital R, and the ds is r squared sine theta, d theta, define R hat. Just along or over the curved surface here, the normal vector is pointing outward from the origin. So the unit normal vector will be R hat. Then we perform the dot product between the vector field and ds. So here, because in the spectral coordinates, the R hat, theta hat, and phi hat form an orthonormal basis of the coordinate systems, which means our hat dot our hat is 1, but our hat dot theta hat and our hat dot phi hat are equal to 0. So in the dot product here, only the R component in the vector field will survive. And then the domain of integration will be from, for theta, it will be from 0 to pi over 2. And the phi will be from 0 to pi over 2. Then after taking the dot product, we have this expression, the R squared to sine theta, and here is a differential area, which is R squared sine theta d theta d phi. And we can do the integration separately on each variable. The phi part here will give you pi over 2, and the theta part here give you 1/2. Then you would get pi out to the power 4 over 4. Then we do the integrals on the surface on the xy plane. So on this surface, the theta is fixed to be pi over 2, and the differential area ds is r dr d phi theta hat. Yes, on this surface, the normal vector is pointing downwards. So because the theta hat is pointing to a direction tangent to the lines that going from the pole here down the surface. So when the theta is pi over 2 here, then the theta hat will be pointing exactly downwards. So similarly, we take the dot product, and here only the theta component will survive. So we have the r squared to sine phi and r dr d phi. And we integrate r from 0 to capital R and phi from 0 to pi over 2. Then we can do the integration here separately on each variables. The alpha here will give you r to the power 4 over 4, and the phi part here will give you 1. So you will get r to the power 4 over 4. Then we do the surface integrals on the xy, on the yz plane here. So on the plane here, the phi is fixed to be pi over 2. And then the differential area is r dr d theta phi hat. So because on this surface, the normal vector is pointing to the negative x directions, and measure exactly the same direction with the phi hat at this point. Because the phi hat is pointing along the tangent, the line along the curve here from x to y along the curve here. So when the point is at phi to the power 2, then the phi hat will be pointing exactly to the negative x direction. Then we do the dot product, and here only the phi component will survive. And the integration is done from R going from 0 to capital R, and then the theta goes from 0 to power 2. Similarly, we can do the integration separately on each variable. The alpha here will give you R to the power 4 over 4. The theta part here will give you 1, but don't forget the minus sign here. So you get minus R to the power 4 over 4. And finally, we do the integrations on the surface on the XZ plane. So on this plane, phi goes to 0, and then the differential area is minus R dr d theta phi hat. The reason of having the minus sign here is because the lower vector of this surface is pointing to the negative y directions. And when you consider the orientation of the phi hat here, which pointing along the tangents into this directions, then for the normal vector here, it has to be minus phi hat. So that's why we have the minus phi hat here. And then we do the dot product between the vector field and the ds, and here only the phi components of phi. So we have the r squared cosine theta sine phi. But here the phi component is 0 when phi is equal to 0, because sine 0 is 0. So the integrand is 0, and therefore the whole integral is 0. Then we combine the results from each surface together to get the overall closed surface integrals. And the r to the power 4 over 4 here will cancel, and you would get a pi times r to the power 4 over 4, which is exactly equals to the result that we get from the volume integrals. The final question is about applying the Gauss law to compute the electric fields both inside and outside the sphere, each of radius a, and has a total charge q. So you're asked to consider 3 different cases. One is a conducting sphere, and one is the sphere with uniform charge density, and one is the sphere with charge density varies radially and proportionally to r to the power n, where r is taken to be greater than minus 3. Then after you have completed all of the calculations, you can try to sketch the variations of the electric fields as a function of the radius for the first 2 spheres, and for the last sphere, you can try the case with n equals to minus 2 and plus 2. So here is the Gauss law. The Gauss law relates the electric flux to the charge that contains in the surface. So here is the integrals of the electric field over a closed surface, and this quantity is the so-called electric flux. So here is the surface of the charged sphere that we are considering, the solid line here, and then we can draw a surface to do the integral here, and such surface is the so-called Gaussian surface. So when we consider the electric field inside the sphere, we will draw a Gaussian surface inside the sphere. And when we consider the electric field outside the sphere, we will draw a Gaussian surface outside the sphere here. So, but the Gaussian surface can be of any arbitrary shape, but there are some shapes are more convenient than the others when we do the calculations, because the system here that we are considering is spectrally symmetric. Then it will be more convenient for us to use a spherical Gaussian surface. And because the system is symmetric, so the electric field will only has a radial component, which is the ER out here. And also the electric field will only depends on the radius r. And also here the differential area dA is simply dA r hat. So because on a sphere the normal vector is pointing outwards from the origin. So the unit normal vector here is simply r hat. Then we can do the integrals in the left-hand side because over a Gaussian surface, the electric field here is constant. So when we do the integral here, it is just the electric field that on this Gaussian surface multiplied by the area of this Gaussian surface, which is 4 pi r squared. Suppose we have a Gaussian surface with radius r here. Then the left-hand side is epsilon 0 ER 4 pi r squared. The right-hand side is the charge that contained in this Gaussian surface. Then after rearranging the terms, you can get the equations 63, so which is simply the total charge contained in that surface with radius r over 4 pi epsilon naught r squared. Then in the first case, we have a conducting sphere. For a conducting sphere, the charge is free to move. So in equilibrium, the charge will distribute uniformly on the surface of the sphere. So inside the sphere, there will be no charge. So when you do the integrals inside the sphere, the total charge will be 0. And then when you do the integrals with the surface outside the sphere, which means you have a surface that completely encloses the charged sphere, then the result is simply the total charge that carried by that sphere, which is Q. And therefore, the electric field inside the sphere will be 0. And outside the sphere, it will be Q over 4 pi epsilon naught r squared. The second case is when we have an uniform charge distribution. So here we have the rho to be simply equal to the total charge Q over by the volume of the sphere. And therefore, the integral here, when it's inside the sphere, is simply the density multiplied by the volume of the Gaussian surface, which is 4 over 3 pi r cubed. Then we get the charge contained in the Gaussian surface inside the sphere to be equal to Q times r cubed over a cubed. When it is outside the sphere, it's simply Q, which is the total charge. Then we have the electric field inside the sphere to be QR over 4 pi epsilon naught a cubed, and when it's outside the sphere, it's Q over 4 pi epsilon naught r squared. Then the last case is when we have the charge distribution varies radially and proportionally to r to the power n. So we can write the rho to be equal to c times r to the power n. Here c is a constant. So the first thing we have to do is to normalize the rho because the total charge is Q. So when we integrate the density over the whole sphere, we will get the result to be exactly equal to Q. The C, R, N here is the density, and the 4 pi r squared dr is a differential volume. Then we can do the integration, and you should be able to get the Q to be equal to 4 pi c e to the power n plus 3 over n plus 3. So after rearranging the terms, you will get the constant c to be equal to Q times n plus 3 over 4 pi a to the power n plus 3. Then inside the sphere, we do the integrations over a Gaussian surface inside the sphere. Then we will computing the charge that contained in that surface. Then simply we do the integrals, and here the CRN is a rho, and the dV is a 4 pi r squared dr. Then we plug in the C that we have computed in the previous slides, which is this term, and the 4 pi is being cancelled. So we only left the integral here. Then you should be able to get the result to be Q times R to the power n plus 3 over a to the n plus 3. And therefore, the electric field inside the sphere will take the form Q times R to the power n plus 1 over 4 pi epsilon naught a to the power n plus 3. And for the case of outside the sphere, we have the total charge if the charge contained in that surface always equals to the total charge of the sphere, which is Q. So the electric field would be equals to Q over 4 pi epsilon naught R squared. Then you, after getting all the results, you can try to plot the electric fields together. And here, the solid line here is the distributions, the variation of the electric field in the conducting sphere. And for the blue line here is variations for the uniformly charged sphere. And then for the black line here is the one with the radially varying charge distributions, and also n is equals to -2, and the last one is the one with n is equals to 2. So inside the sphere, you can see the one with the radially varying charge distributions, and n equals to -2 is the strongest, and the second one is the one with uniform charge distributions, which the field varies linearly, and the next one is the one with n equals to 2, and the last one is the conducting sphere, which has 0 electric field inside the sphere. But outside the sphere, all of the distribution will give exactly the same electric field. So no matter how the charge distributes on that charged sphere. And that's it for today's exercise class. So if you have any questions, just feel free to contact me about email. Thank you.